All right. Any questions from homework, quizzes, and exams? Austin.
Can you go over 3.6, problem 11?
3.6. 11. I think we went over something similar before, so I will just write down the answer, and you stop me whenever you see something that is confusing. Copied the wrong thing. Why did I copy the wrong thing? I think it's here. Arrow. 11? 11. Whole thing times y. Mm-hmm. Any questions, Austin?
No.
Looks good. Okay.
Yeah.
Anton?
So I had two kind of like general questions. My first question is, when you're doing like implicit differentiation, why is the answer there like helpful to have like an x and a y in the derivative?
So again, when you do implicit differentiation,
you end with like the y1 equals, and then there's both x variables and y variables. Why is it helpful to have like? I get
actually,
that.
Okay, let's say this. Let me decompose your question. Let's take an easy one. This is the circle. Your question is, why is it helpful that there is x and y here?
Mm-hmm.
Okay, instead of just purely x.
Yeah.
Which in this case, actually, we can do it. It's actually x over square root of 1 minus x squared.
Okay, yeah, I guess you can.
Right? Now, two things. Number one, it's a circle. What's the derivative at x equal to 1/2? You have two answers.
Yeah.
So can you see that your derivative not only depends on x, but also depends on y,
I guess in this example that makes sense.
right?
Just for the more
That's
complicated ones, it looked weird, but
yeah, this is number one. So even if both are doable, this one give you more information. Okay, if
yeah.
the derivative depends also on y, because usually you don't have a function anymore. You have something, if you pick x, you have multiple y. So what do you mean by the derivative at 2? You have 3
Oh,
points. You have 3 derivatives, right? Which one?
okay.
Well,
Yeah,
you
that
need to
makes
provide
sense.
me additional y number. Number 2, something like this. You don't even know then how to finish the problem with x and y and eventually replace your y to be your x. There's simply just no way. So in that case, you have 2 choices. The first one is something with x and y. The other one is only x, and this is not even doable. It's impossible. Because to do that, usually what we do is we find this one first and replace all the y by x. But
Yeah.
can you even solve y from here?
No.
So that's why. Okay.
Okay.
If you don't
Sweet.
have implicit differentiation, you need to solve y from x first. In
Yeah.
general, number one, that is hard. Number two, it's impossible actually
Oh, okay.
for a lot of cases. Very good
Sweet.
question.
That makes sense. That makes sense. My other question was just
So hold
kind of
on.
like,
So just
oh,
to be
sorry.
clear, we're
Yeah.
not picking this one because we like it. We pick this one because we don't have a choice.
Right.
Okay.
Yeah.
So
'cause
if
need
you
to
could
get-
do this, of course, go with that. It's
Right.
just in general, it's not doable. All right. Yeah.
Sweet.
Second question.
My other question was like on the exam, how much simplifying do you want? Is it fine if it's in a really complicated form?
Actually, it's better if it's in a more complicated form.
Right?
Because if I see a simplified form, 2 things may happen. Number one, and it's wrong, okay? Then 2 things may happen. Number one, you did the wrong differentiation. Number 2, you did the right differentiation, but you did the wrong simplification. If you
Yeah.
just write down the final answer, there's no way I know which one. Because the first one is going to cost you the majority of the points. The second one will cost you maybe just 1 or 2 points.
Okay.
Okay, so I would say keep everything, especially when you do quotient rule. It's a long thing, right?
Yeah.
Okay, so keep the original thing so I can see clearly this one clearly come from a product rule because I see 2 terms.
Sweet.
Okay, so
Thanks.
that's for exam. However, I will give you an example like this. Find y prime prime of okay, let's do it together. It's not too difficult. Y prime is 1 over this times the derivative of this. Which is, now here's the problem. You are going to take the derivative again, right?
Yeah.
And this already looks freaking complicated with a product rule, 2 things together, and all the crap. So you can keep things like this and start doing the derivative, or you can simplify a little bit before you proceed further. Then you realize they cancel. So the second derivative is just going to be this. Sounds good. So in this case, I strongly suggest you don't have to do the simplification if you are going to take the derivative again, simply because the thing may look easier. You know, so it's up to you. But I personally say, if you're taking the derivative, and you can do some algebra before that you take the derivative to make the whole thing look a little bit simpler, definitely do it. Okay, you don't have to, but definitely do it. And then if you have an answer which looks like this, you don't actually have to simplify anymore. If this is the final answer already, I would say just, yeah, I know you can simplify it, but it just takes some extra time, which I don't care. Okay, so let's just stop your answer there.
Sweet.
Mm-hmm. What did I do here? All right. Yeah, speaking of writing, by the way, I was giving example to the other class. about a problem which we didn't do. Okay, something like that. For example, if you end up with this. Okay, your answer should be this. Okay, do not do this. If you just give me this as the answer, which I know clearly what you mean. Okay, but don't do it. Write your answer in a formal, careful, and complete way. Do this instead. Make sense here? They mean the same thing, but the first one you're showing me, hey, think about this. Are you going to give this to your client or to your boss and say, you know, I put the process there. You just do the dividing yourself. It's not hard. Please go ahead. You know, that's not some attitude you want to give to your client and just like, hey, this is the answer. If you would like to see my step, this is how I got it. I divided, right? But you're not going to say, hey, this is basically done. You just use this number plus that number, divide whatever number you find. That will be your answer. And the client would definitely just complain about you and just say, this guy didn't give me an answer. He asked me to do it myself. Why should I pay for that? Okay, things like this. So make sure you write your steps like that. Try to avoid things like this. Okay, try to avoid, you already got to this step, but you just say, hey, times y, period. Well, write that thing down. Okay, write the complete answer. Other questions regarding the exams, web work, anything? If you haven't done so, I know the 3.6 and 3.9 are due this Saturday, which is after the exam, but they will be covered in the exam. So make sure you do all the web works before the exam, even though it's due after. You need some practice. Okay, everything we have so far is not difficult, but it's complicated. You need to get familiar with it. You need to get more experiences. So try to practice a lot. No more question? All right. 3.9, we finished. Related rates. It's a very standard problem. Now you can see, you know, the real problem can be all kinds of things. You can talk about shadows. You can, with a spotlight, you can talk about boats. You can talk about carts, whatever. There's really no uniform way to tell you which problem you will see. Okay, so we can only teach you the procedure. After that, you're on your own. You will see a lot of formulas like arc-length formula, which are necessary. Circle, both area and the perimeter. Like sphere, volume, surface area, triangle, rectangle, whatever you have learned before in junior high and high school. Okay. A big question I keep receiving is, should we know it? Okay, a big question I keep receiving is, should I know this? Okay, you may have different answers. Number one, you need to ask yourself, have you learned it? Have you seen them before? If the answer is yes, why shouldn't you know it? Do you want to claim that you take any class and as long as you're not taking it right now, it's okay for you to forget anything that covered in that class? Sounds good. Okay, so I don't put those kind of formulas into the exam simply because I don't want to go over those kind of hustles of arguing with people. Well, I'm not obligated to know the formula of a sphere, its volume. Okay, but really, you shouldn't be proud of not knowing. Sounds good. So that's the comment I give you guys. Even if you don't want to memorize it, I won't say it's okay. It's not okay, but I can't force you. Okay, and I don't want to go over the hustle that I need to force you to remember that thing in the exam. I just don't want to go over the hustle. I don't put them in the exam, not because I don't think it's important. I just don't want to go over the hustle. Okay, But at least your attitude should be, you are not proud of not knowing them. You shouldn't think it's okay for you to not knowing them. Okay? Because if I see a guy ask them, well, what's the derivative of sin x? They say, well, let me look it up. The first question came to my mind is, have you taken calculus? If you take a calculus and you don't know the derivative of sin x, what did you take there? Did you actually pass it? Have you actually applied yourself there? Kind of makes sense here. Okay, so I'm not saying like you need to memorize everything you have seen before, but at least you should be familiar with some of them. And if there's something that you're not familiar with, at least you should not be proud. Okay. Second thing is for the major ones. For example, there are some formula which you don't use very often. For example, maybe a lot of you won't remember the derivative of a log function when you have a base other than e. Okay, because we don't use that thing very often. We probably did 2 exercises on that for the whole semester. Sounds good? But it will be really trouble if you don't know the derivative of the one with log e, because we use that thing on a daily basis. So at least when you finish your class, and if I ask you in 3 years or 2 years, you should be able to reflect. You've learned this before, and you should be able to reflect at least half the important formulas you covered in that class. You may miss some small things, but you should at least remember the major structure. Okay, that would be what I call you learned some classes. Otherwise, I mean, you go to Calculus 2, you say, well, this is something I heard in my Calculus 2 all the time. It's just like, it's been a while for me to take in Calculus 1. So sorry, I don't know any derivative you refer to. Or if I go to differential equation, people will say, sorry, it has been a long time since I took calculus. I would say, I don't know how to respond to that. You know, if you become an engineer, you want to build some engine, and you say, sorry, it's been a while since last time I used a screwdriver. I would say, well, why are you here? Sounds good? Okay, so be prepared for yourself. Should you know it? Now I want to give you a firm answer. Yes, you should. There are some common sense you should know. You should know Shakespeare. You should know the earth is not flat. Even though you don't major in that. Okay? But of course, I won't cover it in the exam. That's my compromise to the education system here. Well, different people have different opinion. I am personally I'm a person who strongly believe that if you don't have the basic, there's no way for me to talk about anything beyond that. Maybe some other people may think you can look up the basics. So we are just going to teach you something beyond. I've never seen nothing work in my life. Okay, so maybe I'm biased, but I think you should start from the basic before you go beyond. That's the first thing. You will see a lot in the homeworks about how to do related rates. You'll see similar triangles, you know, something you learned before. The second thing is just application I want to show you. It's a story. Okay. It's not the rigorous scientific story. This is something I heard. It's actually an anecdote I heard from people. Story about GPS. How people invented GPS system. Okay, it's a very interesting story. I can't guarantee it's true. Basically, it's a group of physics students. I don't remember, it's in MIT or Cornell, some top school. Okay, they just finished the physics exam, so they were exhausted and say, let's relax, you know, take a break. And the way they chose to take a break is doing some mathematics problems for fun. Okay, sadly, but that's how they chose it. So what happened is during that time, NASA just launched a satellite. They become excited and so they look up all the parameters in the paper, a newspaper, and they say, wow, how about we just send the signal to the satellite and see if the satellite actually responds to our signal. So what they did is actually they sent a signal to the satellite, and then the Earth rotates, of course. After a while, they receive the signal sent back from the satellite. And of course, the satellite is also moving. Sounds good. Here's an interesting thing. They decided, well, we know how fast the Earth is moving. And we know the relationship between the radius of the Earth, the orbit of the satellite, and things like that. So we can set up an equation between them. Can we use all this information to figure out how fast the satellite is moving? Do you see a related rates? Because you have two rates, and certainly they are related by the Earth and orbit of the satellite. They did the calculation. They find the speed. It was amazing. The speed matches what they found in paper. They were super excited. They told their professor and say, hey, this is what we find. Now, as a professor, you always tell the student, now go find more. And the professor simply said, well, if you can do that, can you do this? Because you always know how fast the satellite is moving, right? By knowing that and sending signals to the satellite, can you know how fast you're moving on Earth? And this time, you don't have to actually move with respect to the Earth. Okay, you can actually move freely on the Earth. You always have some speed, right? So you have another related rates problem. And what do you say? It's pretty easy to do. It's basically the same equation. Before you know dA over dt, you want to find dP over dB over dt. This time you know dB over dt, you find dA over dt. It's pretty easy to do, right? Now, do you see what's going on here? You launch the satellite. You know all the parameters about the satellite, including the speed of the satellite. Now, by sending signals to the satellite, you will know how fast you are moving on Earth by related rates. That is GPS system. Global positioning system. So how fast do they calculate how fast you're moving? How do they do that? They do it by related rates. Okay. They assume they know how fast the satellite is moving. They know how fast you're moving on Earth. Sounds good. They had this wonderful problem. They talk about it. The military heard about it. The military came here and bought the whole thing. Okay, you guys just do the development for us. And then they eventually developed this system. Of course, at first, this one cannot be used. Why? Because there's always an error. Systematic error. They could never get it accurate. It's always like several digits off. But then what they discovered is you need to adjust. For special relativity. Okay. Does anybody here know special relativity? Heard about it before? Roughly, it's from Einstein. He did special relativity and general relativity. That's basically his biggest work. What's the conclusion? Conclusion is very bizarre and simple. When you travel at a high speed, like the satellite, your time slows down. Have you seen something like this before? That's amazing. Like when you travel really, really fast, your time slows down. If you travel at the speed of the light, your time basically freezes. That's how you can actually live forever. As long as you just keep traveling at light, you basically don't age at all. Okay. So it turns out you have to adjust for special relativity and general relativity because with on the satellite, okay, the clock is actually slower than it's on Earth. People actually did an experiment on that, which is super interesting. Think about it. It's crazy. Albert Einstein has something that you cannot verify by experiment because nothing travels that fast, so you can see a difference. Still okay? So what they did is actually they waited until they have atomic clocks, which are super accurate. So they put the two together, anchored them to make sure they are actually all aligned together. Okay? Then they put one on an airplane and let the airplane fly against the rotation of the Earth. That is very fast speed. Sounds good? They let it fly for a while. They actually let that thing go down. Your clock are aligned together before you go. And they are super accurate, but turns out actually one slowed down. And how much did it slow down? It matches exactly what Einstein calculated. Sounds good? So that's actually how we know relativity is true. Time does slow down. another crazy stuff what Einstein did was, you have the sun. Sun is a big mass, very, very heavy. Doesn't distort the space according to his general relativity. And what he claimed is, if you have a light coming here, and because the space is distorted, your light is going to actually bend. You're supposed to go this way, but you got bended by the distortion of the space. Make sense so far? That's how he explained gravity. But how can you verify that? Well, that's pretty easy. You just take the sun, and this is the Earth. You just look. There is some star far, far away. They send the light towards you. Still okay? And then you will be able to actually see the thing is going to be different. So you will actually mistaken the star is here. While you actually know the star should be here at the same time. Then you know how much it bended. Sounds good? Problem is the sun is so bright. If you just look at the sun and try to discover some light behind the sun, you'll observe nothing. Still okay? So how are you going to solve that? Wait for eclipse. I don't know if is that how you spell it? Eclipse. Man. Yeah, eclipse. Wait for eclipse. So they sent two groups of scientists during eclipse, maybe in 1920 something. Okay, they actually went there. Two groups all observed the sun at the same time from different angles. They find that the bending angle matched Einstein's calculation. Okay, that's the moment they know Einstein is correct and Newton is wrong. Okay, so that's actually how they did it. It's pretty amazing how human can achieve such things. Every time you think about a story, it's just amazing. Like, how are you? I mean, remember, this is the 1920s. They don't have the technology. They just go there, okay? And maybe they go to a small town. The small town will never have people. So many people visiting other than an eclipse. Okay, so suddenly a lot of big guys came to that town. You know, originally the town has 100 people. Now they have 400 people, 500 people from all the places coming here. They hire people to draw. They hire people to take photos. Okay, they have restaurants. They have hotels. It's like a festival every 70 years. Okay, so that's actually how they did it. And during that time, you have something even more crazy. That is like you got two people, now back in then, who was in war? Two countries, I don't remember which one, but basically they just said like, I'm your enemy. I'm your enemy because my country is having war with you. But I'm a scientist. Okay, so can I actually go to your place and observe the eclipse? Simply, I cannot do it here. Okay, and they actually allowed that. They actually stopped the war to let people come there and just look at eclipse. Okay, that's some amazing stuff we have done before. By the way, if you're interested, you can really see, you should really Google. Did you guys know that 2 years ago or 1 year ago? I don't remember. We actually observed the black hole. We took a picture of it. Okay, the black hole one. You should really see how people collaborated on that thing. We basically built a big lens, which is bigger than the size of half the Earth. Okay, and try to observe the black hole. You require 7 different countries to work together at different locations with their telescope. Okay, but either way, Google it. Picture. It's amazing how people work together across the planet. Okay, Google it. How they did it. How do you build a lens which is half the size of the Earth? Okay. All right, so that's just some applications of related rates for GPS. From now on, you can actually think about all kinds of things you have in your gadgets. If you take out your smartphone, okay, this smartphone here, how much technology is in? And you should really think about how much mathematics is in, how much calculus is in. Okay, I can already think about 5 different things that requires calculus in order to make this phone work. How to design an antenna, for example, you need to use fractals. How to analyze the signal, you need to use Fourier analysis. So all those kind of things. And then, of course, you don't know that much technology for now, but at least you should think about where related rates can be applied. For example, I did it in another class. I didn't do it here. So let's say you have a pirate ship. Okay, coming towards you. Okay. So what do? Usually you have a watchtower. You have a person standing there, taking a telescope, or just use your bare hands to look at how fast the ship is traveling. How do they do it? Basically, what they do is actually they measure the angle of elevation, depreciation. After a while, it becomes this. Can you see the angle actually changed at a certain rate? Okay. According, a really experienced watcher will be able to actually guess or calculate or analyze how fast the ship is traveling by how slow or fast he moves down his angle of differentiation. Okay, that's exactly related rates. There's no confusion there, right? Just the same thing we did with the airplane. Okay, so it's actually used a long time ago. Very useful. All right. You can try that yourself by seeing the angle of elevation moving. Try to estimate how fast a bird is traveling. Okay, if you just look up, see a bird, a line you were saying with the bird traveling in a straight line, see how fast the bird is traveling. Okay, it's gonna be super interesting. Okay. And now if you can look even further and longer, you can measure how fast a star is traveling, a planet is traveling. Okay, it's the same thing. It's just we have a better equipment other than our eyes. We use telescope. All right. Any questions before we move on to the next section? All right, let's move to 3.10. This is what we have. Linear approximations. Question, what is square root of 4? 2. Everybody knows? Great. What's the square root of 4.1? Number 1, it's not 2. Number 2, it's not 3. Still okay? It's going to be close to 2. Now, how close is it? 2.5? 2.3? 2.1? 2.05? Things like that. Sounds good? Okay. Now we clearly have something. That is, number 1, we know the value close to you, and you just move a little bit. What I'm expecting is you're just going to be 2 something, and you don't move much from 2. Okay? Question 2, I want to know how much. Sounds good? This is actually how your calculator does things. How can they do the square root of 4.1? They rely on the square root of 4. Okay, and then they adjust it a little bit. Okay, how do we do that? Well, let's think about it. Here's 4. Here's 2. You know everything here. Sounds good? Here's 4.1. It's technically very close to each other. I'm just going to draw it a little bit further to illustrate the idea. Okay. What you really want is this point. And of course, you don't know how to do it. Sounds good? So instead, you did this. What you can do is you can find the tangent line here. That's all right. You take the derivative, do whatever, right? Then what you did is you locally replace the curve by a straight line, not far away. Then what you do is you use the point on the straight line instead and try to say, that's my guess of the red point. From here, you can see it's not accurate. Sounds good? But it's not too far away either. So that's going to be my approximation. It's not going to be accurate, but it's going to be close. Does it make sense here? All right, let me write down the steps. Our goal is find this. What do you do? Number one, using the information at 4, because 4 is nice. Okay, what do you do? Number one, you find the tangent line at 4 because it's easy. Let's call it Lx. Okay. Number two, Lx is different from this. We just use L 4.1. Sorry, square root of 4.1. Note, I cannot say equal because technically it's not the same. So what we know is we use approximately. It's roughly this. Is that clear? Let's do it. The first one, you know how to do it. You have y equal to square root of x. Find the tangent line at 4. That's easy. Solution. I need a point. That's going to be 4, 2. I need a slope. That's y prime. Okay. At 4, your slope is going to be. So together, the tangent line. That's my Lx. Still okay? Now what I'm going to do, I'm going to use L 4.1, which is super easy to compute. Sounds good? Okay. What's the relationship? Number one, is Lx the same as square root of x? No. They are roughly the same at 4. Okay. Then, will this one be the same as this one? No, but roughly close. So that's my guess. Actually, not guess. That's my approximation. Sounds good? Okay. Everything we just did, we used the derivative, tangent line, linear function. We can plug in and find any values. This is the number we want. We had. Okay. What's the real number? Well, let's take Wolfram or calculator to figure out square root of 4.1. The real one is, I'm coupling from Wolfram, it's 2.0248 4567. Okay. Are we good? Pretty close. Okay. What do we rely on? We rely on locally, I can replace a function by a line. Everything with a function is hard. Everything with the line is easy. How do I find that line? I use derivatives. Still okay? Is the approximation going to be good? It depends. The closer you are to this 4, for example, I did 4.1, but if you want to approximate 4.05 using the same method, this one is going to be more accurate because you're closer to 4. Still okay? 4.01 is going to be super accurate because you're even closer to 4. The closer you are to this position, the better. That's roughly the idea of linear approximation. We approximate the function with a line. Sounds good? All right. With the same idea, can you find sine 46 degree? What do you think? Let's go with 45 degree. And you're only 1 degree away. Still okay? Go to 45 degree. What am I going to do? I'm going to draw this. This is 45. I'm going to draw a straight line here using all the information from 45, which I can do by taking the derivative, by the way. Okay. Then I'm going to say this is what happens at 45. 46 degree is here, but really I'm going to use the thing on the red line instead. That's not going to be a bad approximation. Sounds good? Can you do this? I'm going to use the info from 1. Again, locally, straight line. Value on the line. It's not accurate, but it's close. All right. Is the idea clear now? What we want to do? Now we just want to give you a formula. Basically, it's just repeat what we just did, but for any function. So, what do you mean by linear approximation? Okay. It basically means locally replace a function fx by its tangent line. Of course, how do you find the tangent line? You take the derivative and do all the stuff we learned. That's why it's in chapter 3. We use derivative, of course. Okay. Then what's the formula? Well, the linear approximation. Of fx at a. Why I say locally, that's what I mean. That line won't work for anywhere. It only works for the first example we gave. It only works for 4 and the things around it. Still okay? If you want to approximate square root of 10, please use 9, don't use 4. Because you're so far away from that, anything can change, right? The closer, the better. Still okay? Now, what's the formula for linear approximation? Well, we can easily do that. We need a point. That's going to be a, fa. We need a slope. That is going to be fa derivative. Still okay? Then the Lx, which is the linear approximation, is nothing but y minus fa equals f prime a x minus a. Or more precisely, Lx equals fa plus f prime a x minus a. That would be the formula for linear approximation. You can either memorize it, or you just simply do the finding tangent line exercise, and they produce the same answer. All right. Is everything clear here? So if you memorize the formula, you can use it now. Let's do a simple example. Find the linear approximation of y equal square root of cube x at 1, and use it to approximate cube root of 0.98. All right. Before you do it, you know this is going to work well because 0.98 is so close to 1. So we're going to have a nice approximation. Number 1, find Lx. You need Fa, which is just 1. You need F prime A, which you need to calculate F prime X first. And then you want to plug in 1. Then by the formula, now you know this one only works for 1 locally because you did use the information 1 for your A. Now let's finish. Up to now, linear approximation is done. Sounds good? Okay. Then what about this one? Well, it's approximately this one, which is why do I do that to myself? I guess there's no way to simplify. That's my approximation. All right, to check our answer, of course, this is just for fun. It's not required by the problem, and you are given a calculator. Otherwise, you cannot check. You have just accepted. This one is 149 divided by 150. Which is roughly, let's take 6 digits. Roughly this. Now let's see the real one. To the 1/3 power. The real one is Sounds good? Okay, this is called linear approximation. Roughly, this is how your calculator does stuff. They don't know square root of x. Instead, they do the approximation. But if they take the approximation to be as good as they can be super accurate. Sounds good? How do you make it accurate? Number one, take up x close to a. Why? Because we said so. If you know all the info at 1, then you do a better approximation for 0.99 compared to 0.98 compared to 0.05, which is very far away. Then you're going to lose it. You're going to lose the approximation. Sounds good? Second, even for 0.98, which is close enough, which you already have some really nice accuracy, but really what you want to do is you want to push this one even further. You want this one to be even closer to 6 digits or maybe 18 digits. Still okay? Like your calculator does. Your calculator is actually better than, we are only correct for 4 digits. Actually 3 digits, right? What if you want more? You want 18 digits, more accuracy. Well, that's the moment you start to think about, maybe I don't want to use linear approximation anymore. How do you do better? Let's do quadratic approximation. What do you mean by that? That means if I have some function here, what do you mean by linear approximation? Replace it by a line, period. Sounds good? What's quadratic approximation? Locally replace it by a quadratic. Then of course, there's nobody stopping you from doing cubic approximation and keep going. Sounds good? Okay, so what do you require them? Well, for linear approximation, I make sure LA equals FA. LA equals FA. Meanwhile, I can require L prime A equals F prime A. So I have a function. We share the same function value. We share the same changing rate. We're not the same. But at least we have 2 things in common. We're better than no relationship. Sounds good? Okay. What about quadratic? Now you can see the advantage. That is, I can require LA to be FA. I can require F prime A to be F prime A. I can also require F prime prime A equals F prime prime A. I have one more requirement. Sounds good? In this way, quadratic is better. Why? Because you have more things in common with the original function than linear. You have one more. That is the second derivative. Okay? Why can quadratic do this and linear cannot do this? Because if you take a line, what's the second derivative of a line? What's the second derivative of the line 2x plus 3? 0. However you pick the line, your second derivative is going to be 0. There's no way you can change the second derivative. Make sense so far? But for quadratic, you can. Of course, quadratic cannot do the third derivative. So do you see the advantage here for cubic? They are going to have more things in common with the original function. That is the first, the second, and the third derivative to be the same. You keep increasing the order of the polynomial. You have more and more things in common with the original function. And then you become more accurate. That's basically the idea. Make sense here? Okay, so we stop at linear approximation because it's easy, but really in real life, you can do polynomial approximation. Okay. Eventually, you can do polynomial up to any degree you want, and they will be as accurate as you want. Eventually, the error will be 0 if you take the polynomial to be infinite degree. That will be in calculus 2. Okay. All right, that's all for today. I will stay here for questions.